This module will show you how to compare two means using a t-test. A t-test is used to determine if the means from one scale, numeric or continuous variable, is different between two groups. There are two main types of t-tests, an independent t-test and a dependent t-test. Which test is applicable depends on whether the sample being tested is independent or not. Both t-tests are parametric tests and hence parametric test assumptions apply. We need to have normally distributed data, homogeneity of variance, interval data, and independence. This first part of the module will detail how to complete the independent t-test. The independent t-test is used where you have two independent samples or groups on one scale outcome. For example, boys versus girls, two different training regime groups, or say a control versus an experimental group. This is considered a between group design. As an independent t-test is a parametric test, the first thing we need to do is check that our scale variables are normally distributed. When we have a look at our data set, we can see that we have an ID variable. We've got sex with males labeled 1 and females labeled 2, so a categorical variable. And then we have weight in kilos, height in centimeters. We then have a weight category, BMI, which is a continuous variable, age, which is also a continuous variable in years, and then our second BMI, which is a continuous variable. So first, we need to change this weight category to actually be a categorical variable. And you can see that it's not because there is a ruler next to it. So we come across to variable view, and where it says weight category, we change this across to being ordinal, because there is some kind of order to these different values. We can now come back to our main data view screen. And to complete our normality check, we're going to use the 5 continuous variables of weight, height, BMI, age 1, and BMI 2. So a reminder on how to complete this, we come up to Analyze, Descriptives, and come down to Explore. We move across weight, height, BMI, age, and post-intervention. And a little trick here, if you don't like how the labels are showing, you can actually right-click and select Display Variable Names, and then you'll see what you normally see in your Data View tab. If you want to change it back, just click to Display Variable Labels. So let's move those 3 across, and we've now got all 5 in our dependent list. We come across to our Plots tab. We select No Box Plots. We select Normality Plots with Tests, and we want to have a histogram instead of the stem and leaf plot. Click Continue, click OK. We have the first part of our syntax at the top, and then you can see now the case processing summary. So we've got a sample of 10 and there's no cases missing. When we have a look at our descriptives table, we can see our mean, we can see our standard deviation, our minimum, maximum, which all looks normal, and we can see our skewness and kurtosis, which is all fairly close to 1. We keep scrolling down just to examine these variables. They all look pretty good. When we have a look at our tests of normality table, we're wanting to have a look at the Shapiro-Wilk, and we're having a look at this column on the right. And as you can see, as all these values are greater than 0.05, they are normally distributed. When we have a look at the histograms, we're not going to expect these to look very pretty considering our small sample size. And that's shown by the histogram, the PP plot. So this is not showing particularly pretty. These QQ plots aren't looking very nice, and that's because of that small sample size. However, with the normality table at the top, we will assume that the assumption of normality is met and that we can proceed to the next step. If assumption of normality was not met, then we'd be required to use the non-parametric alternative for the t-test. So let's come back to our data view page. In this worked example, we want to know if there is a difference in height between males and females. Now we know that they're going to be independent groups because someone's either, in this case, a male or classified as a female. And our dependent variable is a continuous variable, which is height measured in centimetres. We've checked that height is normally distributed, so we're able to continue. We select Analyze, Compare Means, and we come down to the Independent Samples t-test. We would drag and drop the variables to now populate these windows. So our test variable is our dependent variable or our outcome, which in this case is going to be height. So we move that across. And our independent variable is our categorical variable. So we move sex into grouping variable. Then we need to define the groups. So male was labelled as 1 and females were labelled as 2. And then we click continue. Once we've completed this, we go OK. We have our little text indicating what we've asked SPSS to do. In our initial group statistics table, we can see that there were 4 males and there were 6 females. We can see that the mean height for males was 179 centimetres, while the mean height for females was 156 centimetres. We'll be using this information later when we have to do our write-up. We then come down to our independent samples test. First, we need to review Levine's test for equality of variances. So we need to check that assumption for homogeneity. We actually do this in this first section here. If this p-value is greater than 0.05, equal variances can be assumed. And in that case, you report the first line of information, which I've highlighted here in blue. If for some reason this sig value was less than 0.05, we can still proceed. However, we would be needing to use this second row, which means that equal variances are not assumed. As this Levine's test is not significant, in other words, it's greater than 0.05, then equal variances can be assumed and we will report this first line of the t-test result. To report this information, we may write something along the lines of: an independent t-test found that mean height was significantly different between males and females. T equals degrees of freedom and our p-value. With males on average taller, using the information from our group statistics section, reporting their mean and standard deviation, than females. And then we would also report their mean and standard deviation.